This is example 210. We're going to try to find what the torque is to move this semicircular gate that is submerged in water. So I think to start, we'll do our usual. We'll start with a free body diagram. And so of course the thing we're looking at is the semicircular gate. So we'll consider it to be a single rigid body. So we'll just do somewhat of a circle here. Not perfect, but that's how it goes. And then we can add all of our support reactions. Right? We know there's going to be a support reaction at that hinge there at A. There's going to be an A horizontal. There's of course also going to be a vertical one. A vertical. Then we'll have the torque that we're interested in. Maybe I'll do it right there. That'd be our torque. What else? We'll have something at B, right? That's resting against the side here. So we'll have a we'll just call it B. And then what else? Of course, we have the weight going down. And then we're going to have a horizontal component of our water pressure. We'll call it FH, and we'll have a vertical component. We'll define that as FV, and we'll say it's upward. All right, so I think we'll start by figuring out what the two forces are based on the water pressure. And remember that we can do that by just doing, for the horizontal one, we can just do a projection. And for the vertical ones, we have to see what the weight is of the water that's sitting on top. Now, to see that, we have two different parts. If we think about our little setup here, I'll just draw a line in here. All right, we can say we have the part up here, right, where we get the water pushing down. Right, that's what we have. So we can say we'd have to find the water weight for this amount of water weight, right? But we also know that we have on the surface down here, the water is pushing upward, right? So we have to take all the water that's sitting on top. So that would be something that looks like kind of a rectangle on top, and then that doesn't look like a semicircle. Somewhat of a circle like that at the bottom, right? And so we know that this part on the left, right, that's going to result in our force going upward, and this one was going downward. I'm sorry, right? Because it's the sitting on top. This is the one that goes upward. So if we add them together, then basically we can subtract this top one out, and then all we're left is with the volume of water that we have to find is exactly the semicircle that we can use. Right? So that means that makes it a lot easier to do because it's easy to find the volume of this or the area of the semicircle and then the volume going into the page, and it's also going to be easier to find where the location of the centroid is for that area. All right, let's start. Let's write this out. Right, so we can say FV is then just going to be the depth is 4 meters, or into the page the depth, and we can say we have pi r squared over 2. Right, that would be the semicircle. And then, of course, let's not forget gamma. So that gives us 4 meters times pi times 3 meters squared divided by 2 times 9,810 Newton per meter cubed. And plug those numbers in, we get 176,580 times pi Newton. All right, So we'll leave that pi in there. Maybe we can cancel something out. Now, the other thing that we need, of course, we need to know where the line of action is of this force. Fortunately, we know that for a semicircle, we know that it is right at 4 times r over 3 pi. And in our case, that'd be 4 times 3 meters divided by 3 pi, and that is just 4 over pi meters, right? That would be this distance here. Maybe I'll put it in here. That would be our x bar. All right, so now we have FV and its location. Let's get FH and its location as well. Of course, we know to do that, right? All we have to do is we have to do the vertical projection, and then we can kind of do our, right? That's what this would look like. And we know down here, our pressure is going to be gamma times what's our depth? Well, the radius is 3, so that would be 6 meters. So based on that, we can go figure out what it is. Scroll down a little bit here. So we'd have FH is equal to, because it's a triangle, 1/2 times gamma times 6 meters. And then the length it acts on is 6 meters again, and then 4 meters, because that's how wide the gate is. So that would then be, if you take all these numbers here together, so we'd have 9,810 Newton per cubic meters. We have 36 times 2 is 72 meters squared, meters cubed. So that leaves us with 706,320 Newton. And of course, this is a triangle, so we know we're at, if we're going from the top down, would be 2/3 times 6 meters. That's 4 meters. So we maybe put that in our sketch here as well. We know that this distance here is 4 meters. It's our y bar. All right, what else are we missing now? We have those two are known. Our weight of the gate is given to us. Oh, I guess it's not fully given to us, so let's write that down. W is, of course, then M times G. So it's 30 megagrams, so 30 times 10 to the 3 kilograms times 9.81 meters per second squared. And that gives us 78,480 newtons. All right, what else do we have? So we have all that. Then the reactions we want to find, the torque we want to find. So let's see. So we have all the rest are unknowns. So we have the torque, and the 3 support reactions are 4 unknowns. Of course, that's not going to work. We need to have more information. What is the extra bit of information that we can find? Well, if we think about this, right, we want to put torque on here on this gate to make it just about turn, right? So if that happens, that means that there's not going to be any contact at B anymore, right? So we can say B, let's do that in red, equals 0, because almost no contact. I'll leave it like that. You know what I mean, right? So that's the idea. So now we have 3 unknowns, and we have 3 equations. So that's good. So we could do stuff like, go through and do vertical and horizontal, but in the end, we're not asked what all the extra support reactions are. We're only asked about the torque, so we can just go right ahead and do a moment around A right here, because that would get rid of AV and AH, and the rest is all known. Then we can directly get our torque. All right, so let's do that. where's my blue? We can say sum of moments at A equal to 0. And what do we have? We have, let's start with W. W is turning counterclockwise, and it says it's acting at G. G is 2 meters. So we'd have W times 2 meters. Then we have FH. FH is turning also counterclockwise. And it is, we said, from the top up here to where it acts is 3 meters. That is 4 meters. So from A downward, that's just 1 meter. Okay, so we have plus FH times 1 meter. Then we have our vertical one. Vertical one is turning clockwise, so it would be negative, and the distance was our 4 over pi, right? So we have minus FV times 4 over pi meters. And then let's not forget we have our torque. The way that we wrote our torque here, it is turning clockwise, so it would be negative. Minus T. All right, excellent. So now we know everything in here, we know except the torque, so we can solve for torque, and we're done. So that means torque is equal to, that was negative, so everything here has stays. So we have W times 2 meters plus FH times 1 meter minus FV times 4 over pi meters. And then we can plug stuff in. Right, so we know W was 78,480 Newton times 2 meters plus FH was right there. 706,320 Newton times, well, we had 1 meter. And then minus FV up there is 176,580 times pi Newton, and then 4 over pi meters. Now we can see why we kept that pi in there, because of course it cancels out. So if we stick all those numbers in, we get 156,960 Newton meters, is equal to 157 kilonewton meters. And with that, we have our torque. Right? So we found that if we wanted to move this gate, if we wanted to start turning it, maybe let some of the water out on top there, right, then we would have to put a torque of 157 kilonewtons on there.